Very good morning to all of you, my dear students. I welcome you all for this online platform of hydraulic machine lab. In the in terms of the third unit we have discussed in the previous lecture. I hope from today, at least the direct second year, the diploma students will also try to attend this because in the last week there was an exam for the third semester. So I hope we have to start now our syllabus. What are the remaining factors? Okay. Yes. So that we can wait for them also till time. So in the previous lecture, I already shared with you the what is the recorded lecture of this in terms of the second unit and the third unit of the Francis turbine. Next one is the Kaplan turbine. In the previous lecture, we have introduced the Kaplan turbine. What is the construction working of the Kaplan turbine? Then what are the different classification? What are the parameters for the limitations and the advantages of the Kaplan turbine? What the Kaplan turbine it required? What the velocity triangles diagram? All these we have seen in the previous lecture. So for the today and those who have not able to attend the lecture, don't worry, I will share you the recorded lecture link in the last of this today's lecture, so that we will you will directly cover up this at earliest. Okay. So all the students, don't worry about the and I have already shared with you the fourth semester section A, all the PDF and PPTs of this from unit number 1 to unit number 4. Okay. So that today we have to complete this unit number 3, so that we can on the next lecture we can to start our fourth semester, that is centrifugal pump, right? Yes. So in the previous lecture we have just seen that how what the Kaplan turbine is, and how the working constructions of the Kaplan turbine, what are the different the in terms of the reaction turbine, what the inlet velocity triangle and the outlet velocity triangle. So now it's time to start the numerical, right, on the Kaplan turbine. Shall we start? Yes. So that the other student can also join. Yes. So the problem number 1, a Kaplan turbine working under a head of 20-meter develops 11,772 kilowatt of shaft power. The outer diameter of the runner is 3.5 meter and hub diameter is 1.75 meter. The guide blade angle at the extreme edge of the runner is 35 degrees. The hydraulic and overall efficiency of the turbine are 88% and 84% respectively. If the velocity of roll is 0 at outlet, determine first runner when angles at the inlet and outlet of the extreme edge of the runner, and second speed of the turbine. So this is the first numerical for the Kaplan turbine. Just like the reaction turbine of the Francis, we have already completed the numerical. We have seen the n number of numericals for in the PPT format, right? So what is the purpose of to cover this numerical? Because in your MCQ test or in your MCQ university exam also, maybe some of the points you can be asked for the in terms of asking with the help of this some of the formulae. Okay. So a Kaplan turbine under working under a head of 20-meter develops. That means in this first sentence they gives us the head. Head is nothing but the capital H. From how much the head of that water is to be get discharged. Okay. So that is 20 meter. So capital H equals to 20 meter. And that Kaplan turbine develop how much amount of the kilowatt of power, shaft power? That is 11,772 kilowatt of shaft power. What is that shaft power? Shaft power is nothing but the output power. As you know that what is the efficiency in terms of the output upon input? So the shaft power is the output, because how much amount of water will strike the runner so that the shaft will be get moved, and how much amount of the shaft power can be generated, that is called the output of that turbine, right? So this will be the output power, shaft power 11,772. And what is meant by the input power? That how much amount of the water is supplied or strike on a turbine, that is called the water power. Okay, so the input is water power and output is shaft power. So the efficiency, overall efficiency, if I want to find out, that is output upon input is output in terms of the shaft power and input in terms of water power. Yes. So the diameter of the runner is 3.5 meter. So now we can, in the previous lecture, we have seen what are the two diameters. One is the diameter of the runner and another is the hub diameter. Okay, DO is the outer diameter of the runner and DB is the hub diameter. What is that hub? And at which the moving blades are to be attached. That is called the hub. Okay, or called as a boss diameter. Okay. So the outer diameter of the runner is 3.5 meter and the hub diameter is 1.75 meter. So these are denoted by the DB and DO and DB, capital D suffix O, that is for outer, and capital D suffix B for the hub. Okay, so the capital O is the diameter for the runner and DB is the diameter for the hub, right? Yes. So the next one, the guide blade angle at the extreme edge of the runner. Guide blade angle, what is that? As you know that there are two guide blade angle at the inlet and outlet, right? So alpha is the inlet angle, guide blade angle, and beta is the outlet guide blade angle, right? And what is the different? Another one is the inlet in terms of the edge angle. Edge is nothing but the inlet and outlet edge angle, or the tip angle is called, or the vane angle is the nothing but the theta and phi, right? The inlet is theta and phi. So there are four angles, right? Alpha, beta are the guide blade angle at the inlet and outlet. Theta and phi are the vane angles or the tip angle at the inlet and outlet respectively, right? Yes. So in this numerical, they gives us the guide blade angle of the edge of the runner at 35 degrees. Okay. So that is nothing but the alpha. They directly gives us the inlet angle, extreme edge of the runner at 35 degree. The hydraulic and overall efficiency of the turbine are 88% and 84%. They gives us the hydraulic efficiency 88% and overall efficiency 84%. If the velocity of whirl is zero at the outlet, as we know that if the velocity of the whirl is nothing but the VW2, that the velocity of the whirl VW2 is zero, that means beta is obviously what? That beta equals to 90 degree. So that must be understand. जैसे ही कंडीशन पढ़ते हैं, जैसे ही न्यूमेरिकल पढ़ते हैं, वैसे ही हमारे दिमाग में स्ट्राइक हो जाना चाहिए कि व्हाट द वेलोसिटी ऑफ द व्हर्ल एट द जीरो एट द आउटलेट, दैट मींस द बीटा विल शुड बी द 90 degree, and that means vf2 is equals to v2. Okay, the flow velocity that is equals to the absolute velocity at the outlet. Okay, yes. So determine what they ask in this numerical: the runner vane angles at the inlet and outlet at the extreme edge of the runner. What is this vane angle? Is nothing but the theta and phi, right? And the whatever the angles is available, theta and phi, you have to calculate obviously. And the second one is the speed of the turbine. Speed of the turbine is indicated by capital N, that is RPM, that is revolution per minute. We have to calculate. Okay, so there are the two determine. One is the angle, that vane angles at the inlet and outlet, that means the alpha, theta and phi we have to calculate, and second one is the speed of the turbine. Let me start the numerical. First of all, whenever we start the numerical, just read the numerical from starting to ending. Then after that, write down the given data or the given parameters what is available with us. Okay, and then after that, draw the velocity triangle diagram. Kaplan turbine, as we know that the velocity triangle diagram for the reaction turbine is constant for both the in terms of Kaplan as well as Francis turbine, right? Before that, we have completed the Francis turbine, the same velocity triangle that the inlet and at the outlet. So this will be the V1 is the absolute velocity at the inlet. Okay, that will be thrown in terms of the at the tip of the curve vane of Francis turbine blade. Then at the outlet, that will be the relative velocity due to the absolute inlet in terms of the absolute and the peripheral velocity, that is u1. Okay, so v1 minus u1 is nothing but the relative velocity. So that vr2 is the first outlet. Okay, and due to that vr2, how much that the peripheral velocity at the horizontal direction along the x-axis, that will making an angle of phi. Okay, so this will be the u2, and then after that, how much that the absolute velocity at the outlet v1 v2 is to be get available at the outlet in the vertical direction. So it will be making an angle of phi. Okay, where the beta is equals to zero, that means the vwt equals to zero. Okay, and in the inlet also the same, due to the absolute velocity making an angle with the u1 at an angle of, that is called the guide blade angle, that is alpha, And whenever we know that the absolute velocity v1 should be composed into the into two components, that is of vw1 and vf1. So the whirl velocity at the inlet and the flow velocity at the inlet, that are the x-axis and the y-axis, two components to be get the absolute velocity is to be get dissolved. Okay, and that in terms of the relative velocity, what is the angle which made by the relative velocity is called the Vane angle at the theta, right? And the absolute velocity with making an angle of guide blade, that is alpha, and that u1 and vf1 are will be available. And in terms of the vw1 is also the in terms of the u1 and available velocities. Okay, right now. So the given data we have already written here. The head is 20 sorry, 20 meter. Shaft power is the output power of the in terms of 11,772 kilowatt. Outer diameter of the runner do equals to, that is 3.5 meter. Then hub diameter is db, that is 1.75 meter. Then guide blade angle alpha is equals to 35 degree. And then hydraulic efficiency is 88 degree, 88%. Overall efficiency 84%. Then velocity of the whirl at outlet is 0, that is vwt equals to 0. All right, and using the relation, now how can we find out the Vane angle? First of all, in the previously also we have seen the in terms of the Francis turbine, what are the if I want to find out, first of all, our target is to find out the theta and phi. So if for the theta and phi, we must know the VW1 and in terms of the right and VF1. So for the VF1, we should calculate with respect to the overall efficiency, because we have the relation for the overall efficiency, because in the numerical they given us a shaft power at output, right? So shaft power, if it is available at the outlet or the output, so you can use the relation for the overall efficiency equals to shaft power upon water power, right? Yes. So the shaft power upon water power you can calculate with the help of the in terms of kilowatt. It is available in terms of kilowatt. So the 11,772 what in terms of kilowatt, so it should be converted into the watt. Okay, so multiplied by 1,000 divided by the in terms of the rho g q into h, right? We know that the water power, how can we find out the water power? That is rho g q h. The rho for the water is 1,000 into g is the 9.81, then q is the discharge, right? That discharge is nothing but the area into velocity, right? Into h. H is the head of that water. In the head of this head of the water of Kaplan turbine is available 20 meters, so no need to convert any. Only just we have to convert in terms of the kilowatt into watt. Okay, so multiplied by 1,000. Yes. So that the what is the unknown factor here? Only what is our purpose to find out the discharge, because in terms of the discharge you can calculate the velocity for the flow vf1, and if you got the vf1, then easily you can find out in terms of the other component like theta and phi, right? So our first aim to find out the q, that is discharge. So efficiency of the overall efficiency of the turbine can be find out with the output upon input. So output is the shaft power, upon input is the water power. So the water power is nothing but the rho GQH, right? And in terms of we have to convert it into the watt, that is available in terms of the kilowatt. So multiplied by 1,000. So put the value and get the answer. You our only unknown is here the discharge. Discharge is nothing but the meter cube per second. So please calculate by your own with the help of calci. Use your calci and paper. Just write down this equation and calculate by your own. If it is any mistakes or if it is any wrong answer, please let me know if there is any correction required. Okay, yes. So that is available here. The 11,772 into 1,000 divided by the in terms of the efficiency of the overall efficiency is already gives us at 0.84 into 100 multiplied by 1,000 into 9.81 into the head 20 meter. Okay, so from this equation, you will get the discharge in terms of 71.428 meter cube per second. Now you get the discharge. Now what will can be available? Whenever you will get the discharge, you whatever the formula for the discharge is equals to the area into the velocity, right? So the area is nothing but here the two diameters are available pi by 4, right? Pi by 4 d square is the only formula for to find out the circumference of the circle or the discharge of the pipe. But here the two diameters are available. Obviously, the both the diameters we have to consider. Then what the formula for the area is pi by 4 do square, that is the outer diameter minus inner diameter square, right? Outer diameter square minus inner diameter square. So the formula is pi by 4 do square minus dv square into the velocity. So obviously we have to consider the flow velocity here, that is Vf1. Okay, because as we know from the last two lectures, that is only considering the flow velocity Vf1. Okay, so now what is our unknown factor here? As we know the discharge value, as we know the diameter in terms of the meter, and diameter at the inlet, and the diameter at the outlet diameter, and the hub diameter in terms of the meter. Only just unknown is Vf1, that is the flow velocity at the inlet. So from this equation, we just put the value and get the answer for the flow velocity at the inlet is 9.9 meter per second. Okay. So now you get the velocity for the flow at the inlet. Now you can come for our target to find out in terms of the what the another value for the inlet velocity triangle, that tan alpha. If you directly apply the tan alpha equals to what that equation? Yes, please check this triangle set. Okay. So how can you find out the tan alpha? Tan alpha is nothing but the opposite upon adjacent, right? So the opposite is nothing but the VF is VW1. So the VW1, how can you find out the VW in terms of the VW1? Okay, you just find out this with the help of this tan alpha, because alpha you know well, VF2, that is VF1 equals to VF2, right? Because at the inlet, and that only unknown is VW1. So you will get the VW1 from this equation. Okay, yes. So tan alpha, if I'm applying the tan alpha, then the VF2, that is the opposite side upon adjacent side is nothing but the VW1. So Vf1 is equals to Vf2, because at the that is the velocity for the flow is same for inlet and outlet, and alpha you know well, that is 35 degree. So the Vw1 is only unknown parameter here. So Vw1 equals to 9.9 upon tan 35 degree. So use of calc, in your calc there are available for the tan 35, you can calculate. Okay, and you will get the answer for Vw1 equals to 14.14 meter per second. So now you get the answer for the velocity of whirl at the inlet. Okay, now using, how can you find out again the theta? By using the relation of hydraulic efficiency. Hydraulic efficiency, they gives us what this hydraulic efficiency of the turbine is. The hydraulic efficiency of the turbine is nothing but with respect to the Vw1 U1 minus Vw2 U2 divided by G into H. But here, as we know that the Vw2 is 0, so the only formula is that Vw1 into U1 upon G into H, right? So hydraulic efficiency as we available is 88%, that is 0.88. Vw1 you already calculated earlier step, 14.14. Velocity at the inlet is velocity at the peripheral velocity is unknown, that is u1. Then divided by G and H we know well, right? Only so from this equation, what is unknown parameter? That is peripheral velocity at the inlet, right? So from this equation, you will get the value for the U1, that is 0.88 multiplied by 9.81 multiplied by 20 divided by 14.14. So the peripheral velocity at the inlet is 12.21 meter per second. Why it is required? Because as we know, if I want to find out the theta angle for the tip angle or the vane angle at the inlet and when at the outlet, so you must calculate the u1 and u2. Okay, so first of all we can find out the u1 by this equation, so 12.21 meter per second. Now you can turn over the, now you can able to find out what the theta, that is our main target for to run a vane angle. Okay, how can you find out the theta here? So apply that the tan theta equals to, again the formula is Vf1 upon what the remaining factor Vw1 minus u1 is the remaining of this angle, right? So the tan alpha, tan theta, if I am applying here the opposite side upon adjacent side, the opposite side is Vf1 upon adjacent side is the Vw1, means from the total Vw1 we can minus or subtract the u1, you will get the remaining line, right? So here tan theta is equals to the Vf1 upon Vw1 minus u1. Okay, theta, I want to calculate the theta. Okay, so all the other factors can be removed on the another side of the equals to sign. Okay, so the Vf1 is 9.9, Vw1 is 14.14, Vu1 is 12.21. All the parameters you know. So the all this theta can be calculated by using the calc. So theta equals to tan inverse of 5.13. So you will get the angle of 78.97 degree. Okay, so that will be the answer for the theta. That is the first target. Okay, the next target to find out the phi. How can you find out the phi? Same way. If for the Kaplan turbine, as we know that the inlet, the peripheral velocity at the inlet equals to peripheral velocity at the outlet. So that is U1 equals to U2 equals to U, and Vf1 equals to Vf2, as we already apply that here, the equation, right? So the U1 equals to U2, so and Vf1 equals to Vf2. So again we can jump on the outlet angle, and again we can apply here the tan phi equals to Vf2 upon U2, right? The simple equation, the tan theta, just like the tan theta, here also apply the tan phi equals to Vf2 upon U2. Vf2 is 9.9 and U2 is 12.21. So you will get the value for the phi equals to tan inverse of 0.811, that is 39.035 degree. Okay. Please calculate by your own in your calci, so that the calculation practice should be very well. Okay, so that is the angle at the outlet also. Now we'll get the first target. Clear our first target, theta and phi. Now the second target, what is our second target? To find out the speed of the turbine is given by, what is that speed of the turbine? How can we find out? As we know that the velocity at the periphery at inlet equals to the outlet, that is U1 equals to U2 equals to, what the formula is available, the in terms of the circumference of the, in terms of the pi d is the circumference of the tip, right, into the what is the speed upon 60, pi d n upon 60. What the pi d means, what in terms of the, if I want to find out the speed of the turbine, so obviously the whatever the runner speed we have to calculate, or the diameter of the runner is to be available. Okay, so the pi into do is the diameter of, in terms of outer. Okay, that is called the runner diameter. So the diameter of the runner should be considered. Obviously, that is the outer diameter of the blade, or the vane, right? So the do into n is in terms of the rpm. So the revolution per minute, but our velocity is in revolution per velocity is in meter per second. So we have to use divided by 60, that converted into rpm into rps, that is revolution per second. So divided by 60. Then put all the values and you will get the answer for that. U1 you already available, the U1 equals 12.21 is equals to pi into do, that is 3.5 meter into n upon 60. So from this equation you will get the speed, that is rpm, because we already convert this in terms of the divided by 60. So no need to convert it again, directly you will get the value in terms of the rpm, right? So the that is 66.63 rpm, that is revolution per minute. Okay, so the revolution per minute rpm is our, you will get the rpm in this problem. So I hope everyone is getting this numerical. In this numerical, only the two target is they ask. First one is the in terms of the angle, vane angle at the inlet and outlet, that is theta and phi, and another is the speed of the turbine, that is rpm. Okay, so how can we achieve this speed in terms of the inlet and outlet velocity in terms of theta and phi? For theta, as we know that all, if I am applying here equation in terms of the velocity triangle, so you must calculate all this factor which is available, vf1 and vw1 and u1 and obviously. Okay, so for that theta and phi, we must first of all calculate the vw1, because vf1 is can be also calculated. So how can you find out the vf1? Vf1 can be find out with the help of the discharge, that is q equals to the velocity the area into discharge. So the area here, the complete area we have to consider for the pi by 4 do square minus db square into vf1. So in this equation you get the value for the vf1, that is the flow velocity. For the discharge we have to calculate the hydraulic efficiency, right? So in terms of the hydraulic efficiency we must calculate, or in terms of the overall efficiency we must calculate the we must available the shaft power upon water power. So the water power is nothing but the in terms of the rho g qh, right? So in this equation you can able to find out this. So in this way we have to complete this equation or this numerical, right? I hope everyone is able to understand this numerical very well and try to solve it by your own in your own practice also. So now we will start the second numerical. Okay, the problem number 2. A Kaplan turbine develops 24,647.6 kilowatt power at an average head of 39 meters. Assuming a speed ratio of 2, flow ratio of 0.6, diameter of gauze equals to 0.35 times the diameter of the runner, and an overall efficiency of 90%, calculate the diameter, speed, and specific speed of the turbine. Yes. So there are again the next problem with the higher some of different parameters. Okay. Yes. So it is very interesting numerical now. So what is this Kaplan turbine develops of 24,647.6 kilowatts. So this will be the what? Obviously, I told you that the output is the shaft power. So the shaft power is available here. This value 24,647.6 kilowatt, right? At the average head is again it uses the head of the turbine capital H. It is indicated by capital H equals to 39 meter. Okay, assuming the speed ratio of 2, it uses the speed ratio. What is meant by the speed ratio? We have seen in the while theory lecture in the speed ratio is nothing but with respect to the u1 into under root of 2gh. That is the okay. So u1 equals to u1 into 2 under root of 2gh. So the speed ratio that is equals to ku, right? So this will be the value for ku. The u1 equals to the ku into under root of 2gh. So the speed ratio is available. Okay, ku equals to 2. Then flow ratio. Flow ratio. What is this flow ratio? This flow ratio is again in terms of the equals to the VF1. That is the flow ratio with respect to the 0.6. That is flow ratio is available into under root of 2gh. Okay. Both these equations we have seen in the theory lectures for the speed ratio and the flow ratio in terms of the U1 and VF1. Okay. So this ratio is that is coefficient is available. Okay. Obviously this coefficient is less than 1 or the unity, right? If it is the coefficient 1, that means it is a 100% ideal condition. So this is what the speed ratio and the flow ratio means what the flow velocity and the peripheral velocity is at the actual condition now, right? So the actual condition means less than 100%. Okay. So that is not 100%. That's why they give us the ratio for that. Okay. Yes. Then after this, what they available? The diameter of the boss. What that boss means nothing but the in terms of the just like the previous numerical we have seen the velocity the diameter of the hub. Okay, so that hub is nothing but the boss. Okay, there are two names, the diameter of the hub and diameter of the boss are equal. Okay, so the diameter of boss equals to 0.35 times the diameter of runner. What is this runner? Diameter is db do, right? So there is the equation gives us in terms of the relation for the diameter for the boss equals to 0.35 times the zero diameter of the runner. Okay, yes. So the relation they gives us relation. Okay. Then the overall efficiency is 90%. Overall efficiency, which is the formula for the output upon input. So the output is shaft power upon input is the in terms of the water power is available, right? So the water power is available in terms of this. Yeah. So the 90%. Okay. Then calculate the diameter. First of all, what they ask to find out the diameter. So all the diameter we have to find out the dB also and do also. Then speed in terms of the RPM, right? And the specific speed of the turbine. Okay, so the three factors we have to calculate. First of all, we can find out the diameter. How can you find out the diameter? With the help of the relation it is available. As we know that in the previous lecture also, that equation based on the discharge can we calculate the diameter of the in terms of the turbine and for the outer diameter of the runner and the diameter for the hub or boss also. Okay, so in this equation if I am available the discharge, so the first one is we have to find out the discharge. And in the previous lecture same as the how can you find out the discharge with the help of the overall efficiency. As we know that the overall efficiency of the turbine equals to the output in terms of shaft power upon the water power, and that water power we have to know that is rho gqh. Okay, so we have to convert this. Here again they use us in terms of the kilowatt, so convert that kilowatt into the watt, so multiply by 1000. Okay, or in terms of the 1000 or in terms of this the 24,647.6 multiplied by 1000 divided by rho gqh. Rho is the density of water is 1000, G is 9.81, the discharge is denoted by the Q and multiplied by the head is 39. So in this way you can able to find out what the discharge is available here. Okay, yes. So directly you just put the value and get the answer for the discharge in terms of this equation. So the discharge is nothing but the three-dimensional discharge is meter cube per second. Meter cube per second. Okay. Then after this, the discharge you can find out with the help of this equation. Okay, write down or calculate by your own. Yes. Then in this, if you got the discharge, so the another equation to find out that whatever the diameter of the in terms of the diameter for the outer of the runner minus the diameter for the hub or boss. Okay, so the q equals to the in terms of the area into velocity. So the area is 5 by 4 do square minus db square into vf1. Okay, so here they gives us the relation that db equals to 0.35 times the do. So you can put this dB replaced by the dB equals to 0.35 times the do, and vf1 is already available, right? In that vf1 you already calculate this vf1 with the help of this equation, that u1 and the vf1 you can get the value with the help of the speed ratio and the flow ratio in the above equation, right? So that u1 equals to the equation that flow ratio 2.0 into under root of 2gh as all the values as we know. Okay, similarly for the flow velocity, vf1 equals to the 0.6 into under root of 2gh, that 0.6 into under root of 2gh available the values, then you will get the vf1 also. Okay, so you can use this vf1 in this equation to calculate the diameter. Okay, so the in this numerical it gives us the relation for the diameter db equals to 0.35 times the do. Put this relation in this equation, so the unknown is only do. In this equation you will just put the relation. Okay, so the discharge 71.58 equals to pi by 4 into bracket do square minus 0.35 times the do square into vf1 is 16.59. So in this complete equation, what is the unknown parameter is only one, that is do. So you, with the help of your with the help of calci, you just calculate the value, right? And you will get the value for the do, that is the diameter for diameter in terms of the runner. Okay, yes, diameter for the runner. Okay, so the diameter for the runner you will get, yeah. Then after that, so if you got the diameter for the runner, so ultimately with the help of the relation, you get the value for the hub also, diameter for the hub. Okay, that 0.3 times the diameter for the runner, that is 2.5, right? So the dB will equals to 0.875 meter. So in this way, you get the value for both the diameter of the runner and the diameter for the hub. Okay, dB and the do. Now the next target to find out the speed. How can you find out the speed? With the help of the peripheral velocity equation, that is the speed of the turbine is given by the equation u1 equals to pi don by 60. So do you already calculated by 2.5 meter, and then n you have to find out. So the velocity 55.32 meter per second equals to the pi d n upon 60, because we have to convert this n into rps. Then only you can convert this. That unit should be balanced. Okay, so no need to change the rpm, right? So whatever you will get the answer in terms of the 60 into 55.32 divided by pi into 2.5. So you will get the RPM, that is 422.61 RPM, right? Maybe it is approximate to 423. Okay, that revolution per minute. That is the RPM. Okay, that is our second target, and the next target is specific speed. The specific speed is given by the equation ns. Specific means what? Particular. Particular means for the in terms of shaft power, right? So for the shaft power, how much amount of the specific speed is available, that is the formula ns equals to n into under root of p divided by h to the power 5 by 4, right? So n into under root of p, that p is nothing but the shaft power, okay, which is available in terms of the kilowatt directly, and h is the head. Head is available 39 meter to the power 5 by 4, and n you already calculate the specific sorry, in terms of the speed of the turbine, that the 422.61. So put this speed 422.61 multiplied by under root of 24,647.6 divided by h 39 to the power 5 by 4. You will get the specific speed of the turbine, okay, with respect in terms of rpm. Why this specific speed? Because what? Specific speed is nothing but with respect to the power and the head. Okay, so the power means for in kilowatt, that head is the speed of the turbine is given by that directly for the rpm without considering the power, right? But this is for with respect to the head and the power, we have to calculate the specific particular for the shaft in terms of kilowatt. for 1 kilowatt of the power or whatever the shaft power is available, right? You can calculate this with respect to the 680.76 rpm. Okay, so that will be the output. Okay, yes, so in this way you will get the value for the you have solved these two numericals for the Kaplan turbine. Okay, I hope everyone is able to understand this numerical, because this, and after that the point one is next topic is only the last topic of this numeric this unit, for the unit number 3, that is draft tube. What is the purpose of the draft tube? What is the mean by the draft tube? Draft tube, I told you in the previous lecture also, just like the if it is the Pelton, in terms of the Pelton turbine, so the nozzle is used for the penstock with the help of the spear, right? So opposite to the spear, or opposite to the penstock, that will called the draft tube, which is used to release the pressure as compared it is formed in the turbine sector, right? In the turbine, that will be the used to release the turbine water pressure, right? That called as the draft tube. So this, in this diagram you can able to see that the shaft is in the moving the clockwise direction, so that the in terms of water will be flow inside the turbine with the guide mechanism and the runner mechanism with the casing, and then after that it will be moved the downward direction, that the um, Kaplan turbine as well as the Francis turbine, both the having the draft tube. Okay, what is the purpose of this draft tube? We can see further. What the water from the penstock at the pressure P1, and it will be further improve the pressure and increase the pressure at from P1 to P2, and then after that it will be used by the heavy piston by the weight W. That the total pressure applied to the rotor is nothing but the P equals to the P1 into of P2. Okay, and that will be used and to release that pressure by the draft tube. Okay, so there will be a how much amount of the pressure is released by the rotor, that called be the use and be lifted by the draft tube. Okay, that means draft tube is nothing but the in terms of divergent section or the divergent type of the nozzle. Okay, which is used to release the pressure with the high velocity in terms of the pressure releasing. Okay, yes, so this type of draft tube is available. You can see the conical draft tube. These are the conical draft tube from the outer whatever the headrest, that will the HS, the head of the steam. Okay, so that up to the tail rest. Okay, and then next one is the simple elbow tube. Okay, the next one is the Modi speared in tube, and last one is the draft tube with circular inlet and rectangular outlet. Circular inlet and rectangular outlet. That are the equation. Okay, so the draft tube theory, what the consider a capital draft tube as shown in the figure. HS is the vertical height of the draft tube above the tail race. Okay, then y is the distance of the bottom of the draft tube from the tail race. There are this is the only the concept, right? From the tubing turbine casing, what the height of the draft tube, that is vertical height of the draft tube. Okay, up to the tail race, and then y is the distance of the bottom of the draft tube from tail race. This will be the tail race. Tail race means what? The water level, in the water level. Okay, and below that water level, how much this tube is to be get in submerged? That is the distance is y. Okay, that is the outlet for the draft tube at section 2, and inlet for the draft tube at section 1. Okay. So applying, how can you find out this pressure? How much the pressure will be available, and how much the distance or the that means the y for the distance of the bottom of the draft tube from the tail race, that can be calculated by use of the Bernoulli's theorem or Bernoulli's equation. While applying the Bernoulli's equation at the inlet section 1 and the section outlet for the 2 for the draft tube. So as we know that the pressure energy in terms of the head plus kinetic energy plus bottom energy. So here what is the concept available? The bottom is nothing but the with respect to the head. Okay, what is the difference in between the head at the inlet and the outlet? That should be considered. Okay, so at the inlet, what is that head is available? That is the total, which is the HS, that is the vertical height of the draft tube, plus y, that is the distance of the bottom of draft tube from the tail race. So this is HS plus y is the bottom head at the inlet section 1. Similarly, at the outlet section, so the pressure head P2 by rho g plus velocity head, the V2 square by 2g plus bottom head. So bottom head is available at the outlet is no, but here may be some of the losses of energy between the section 1 and section 2. So that loss here we can consider the HF, sorry, where this HF is the loss of energy between the section 1 and 2. Okay, 1 and 2. So here obviously the bottom is 0, but only the loss of energy can be considered. If it is available in the numerical or any type of the actual condition parameter, so that will be considered here. So the P2 by rho g is obviously the atmospheric pressure head plus y, right? So the atmospheric pressure head in terms of the P2, because it is at the section that will be outlet as compared to the inlet, right? So that P2 by rho g equals to PA by rho g plus y, that can be available here. Okay, so you can find out in this way with the help of this equation to find out the how much the bottom of the vertical bottom sorry, the distance of bottom of the draft tube from the tail rest and all. Okay, yes, substituting that can be calculated by substituting the value for the P2 by rho g in the equation 1. You will get the P2 P1 by rho g plus V1 square by 2g plus the bottom equals to PA by rho g plus y plus V2 square by 2g plus HF. That means the pressure at the outlet of the draft tube is equals to the atmospheric pressure plus the bottom distance from up to the tail race, right? From the tail race to the bottom. Then you can use this HS for the YY can be cancelled for both the side. So the whatever the height of the draft tube can be available HS and equals to the PA by rho g plus V2 square by 2g plus HF is the loss. Okay, so that you can calculate the pressure head by the P1 by rho g, and with the help of all the sides can be another side of the equals to sign. Okay, सभी चीजें जो है इक्वल टू साइन के उधर भेजेंगे। ये है फॉर्मूले अवेलेबल है सिर्फ यही, हमें अगर कहीं पे न्यूमेरिकल आता है ड्राफ्ट ट्यूब का, वैसे आता नहीं है मैक्सिमम, लेकिन अगर आता है न्यूमेरिकल तो उसके लिए हमें प्रेशर हाउ टू फाइंड आउट द प्रेशर ये समझने के लिए ये न्यूमेरिकल है या फिर इसका डेरिवेशन है कि फॉर्मूला है अकॉर्डिंग टू द बर्नौलीज इक्वेशन हाउ कैन फाइंड आउट द प्रेशर हेड फॉर द विद हेल्प ऑफ P1 by rho g is equals to the atmospheric pressure at the outlet PA by rho g minus HF. HF is nothing but the height of the draft tube minus of in bracket the velocity difference in between the V1 square by 2g minus V2 square by 2g minus the head minus the loss. Okay, so that will be the loss of energy. Okay, HF. So in this way you can get the value for this draft tube or the pressure difference. Now the another concept is the efficiency. The last concept is efficiency of the draft tube. How can you find out the draft tube efficiency? So the efficiency of the draft tube, obviously the ratio of actual conversion of kinetic head into the pressure head, that is called the output. Our output is what the actual kinetic head, how much the amount of head required with the help of the kinetic energy, okay, into the pressure head divided by the kinetic head at the inlet of the draft tube, that is the input, right? हमें समझना है कि इफिशियंसी फॉर द ड्राफ्ट ट्यूब अगर कैलकुलेट करनी है तो आउटपुट कहाँ पे मिलता है और इनपुट कहाँ पे से सप्लाई होता है। तो ये दो चीजें अगर हमने कंसीडर की या समझ में आई तो इनपुट आउटपुट कहाँ से मिलता है, जहां पे आपका आउटपुट इन टर्म्स ऑफ द कन्वर्जन ऑफ काइनेटिक एनर्जी, क्योंकि प्रेशर एनर्जी जब काइनेटिक एनर्जी पे कन्वर्ट होती है और वहां से जब आउटपुट मिलता है दैट इज फॉर द प्रेशर हेड, राइट, एट द आउटलेट ऑफ द प्रेशर हेड with the kinetic head difference divided by the kinetic head at the inlet only, right? इनपुट क्या है काइनेटिक हेड एट द इनलेट, आउटपुट क्या है काइनेटिक हेड का डिफरेंस, दोनों में से जितना भी डिफरेंस बचेगा दैट विल बी द आउटपुट, और इनपुट क्या है kinetic head at the inlet of the draft tube. So here the equation that is actual conversion of kinetic head into the pressure head upon kinetic head at the yes. So the V1 is the velocity of water at the inlet of the draft tube, V2 is the velocity of water at the outlet of the draft tube, and HF is the loss of head in the draft tube, right? Whatever the loss of head, because if it is the condition of actual parameter, so the HF should be considered. If it is not, if it is a consider of ideal case, so HF will be equals to 0, right? So what the efficiency of the draft tube can be available, the velocity difference in terms of kinetic head difference. So the V1 square by 2g minus V2 square by 2g minus of HF, that is loss of head in the draft tube divided by the kinetic head at the inlet, V1 square by 2g. So this will be the formula for to find out the efficiency of the draft tube. Okay, and the last stage, what the cavitations in turbine, why the cavitations can be achieved or available or how it is formed, that the cavitations, right? The cavitations is the formation of vapor bubbles. I told you in the previous lecture while cover the theory, right? The cavitation is a formation of the vapor bubbles in the liquid flowing through and hydraulic turbines. The cavitation occur when the static pressure of the liquid falls below the vapor pressure. Obviously, hai, right? If the pressure difference will be available, if it is found, so obviously the cavitation can be formed, because as we know that most of likely occur, it is most likely to occur near the fast moving blade of the turbine and in the exit region of the turbine, that will be the cavity can form, right, called as a bubble, vapor bubbles. And the effect, what the effect of cavitation? The formation of water, the formation of vapor bubbles in cavitation and collapse of these bubbles generates the pressure waves, which can be of high frequencies, so that causing the damage of the machinery. Due to the cavitation, maybe the machineries can be damaged, right? Due to the pressure difference, how much the water vapor bubbles can be formed, and it called as a cavitation, which collapse this vapor bubbles or the bubble generation with decreasing or increasing the pressure waves. If it is the pressure will be changed, obviously, so the high due to the high efficiencies causing the damage to machinery, right? The machine surface are more damaging and the causes the corrosion, right? मशीन सरफेस डैमेज हो सकता है और उससे क्या हो सकता है, कोरोजन भी हो सकता है. So the increase of the noise, that can be increase of the noise and the vibration and the loss of efficiency can be possible. So these are the in terms of the cavitation format, right? Cavitation, तो इसमें हमने कैविटेशन में सबसे इजी क्या है, सबसे अच्छा एग्जांपल है हमारे घर में, हमारे इसमें मोटर यूज करते हैं, हम पंप यूज करते थे. तो कैविटेशन कैसे जनरेट होती है? इफ द प्रेशर इज अवेलेबल विल बी चेंज, एटमॉस्फेरिक प्रेशर और सक्शन प्रेशर जो है पाइप का, वो अगर चेंज हो गया है, वो अगर चेंज हो गया, अगर उसमें एयर गैप आ गई, बबल्स आ गए, तो उसमें से वो कैविटी जनरेट होती है, दैट इज कॉल्ड द कैविटेशन. और उसको हमें रिलीज करने के लिए क्या करना पड़ता है, फिर से उसको प्रेशर को फॉर्म करना पड़ता है, दोनों का प्रेशर सेम करना पड़ता है बाय बाय सप्लाइंग द वाटर, है ना. हम उसमें क्या करते थे पहले, इसमें क्या रहते थे हमारे पुराने पंप में, क्या रहता था कि उसमें एक चाबी रहती थी जिसको हम रिलीज करते थे, सो दैट द कैविटेशन और एयर बबल्स और एयर कैन बी पास फ्रॉम द सक्शन पाइप बाय सप्लाइंग. और हम उसमें क्या करते थे, डिस्चार्ज पाइप में पानी भरते थे, राइट. तो पानी भरने से फिर जो भी अंदर की कैविटी है, जो भी एयर बबल्स है, वो सारी चीजें हम कैविटेशन को निकाल देते थे. और फिर उसके बाद उस चाबी से पानी अगर कंटिन्यूसली फ्लो हो रहा है, तो इसका मतलब वो कैविटी निकल गई है, फिर उसको चाबी को टाइट करते थे. अभी भी आज के डेट में जो नए टाइप्स के सेंट्रीफ्यूगल पंप्स आ रहे हैं, उसमें ये अवेलेबल नहीं है. उसमें डायरेक्टली प्रेशर रिलीज करने के लिए हम डायरेक्टली अगर उसको कंटिन्यूसली स्टार्ट करते हैं, सो इट कैन बी जनरेट द प्रेशर बाय देयर ओन एंड टू रिलीज द और टू रिमूव द कैविटी. ओके, तो ये सारी चीजें हैं related to the unit number 3. So in this way we can we have complete this unit number 3, right? So that in the next lecture or in the lecture for today's only, okay, today itself, please join the today's lecture again, because that lecture will start the centrifugal pump, what is the best numerical or the theory will also available. Okay, so that is up to me for the okay for the today's recorded lecture.